Okay, so let's get started with our 5.2 perpendicular bisectors lesson. In this particular lesson, we are going to learn how triangles have perpendicular bisectors and how that can help us to find missing side lengths. Okay, up to now we've learned what a midpoint is. If you recall, if you have a segment, let's call this segment AB. A midpoint bisects this segment. So a midpoint would be right in the middle. Let's call it P. Since it bisects, that means that it splits it into two congruent parts. So AP would be congruent to PB. So a midpoint bisects. Now, midpoints are not the only things that bisect segments. We could also have a segment bisector, such as a line. So we can draw a line going down the middle of the segment, and that would also, let's say the name of this line was L. Line L would be considered a bisector if it happened to split it, the segment AB, into two congruent parts. So this would be also a segment bisector, but it wouldn't be a midpoint. It would be a line. Now, if this line was 90 degrees, then it wouldn't just be any kind of bisector. It would be called a perpendicular bisector. Perpendicular bisectors are segments or lines that bisect a segment at a 90-degree angle. So let's find out more about that with the official definition. Here it says, a segment bisector intersects a segment at its midpoint. A segment, ray, line, or plane that is perpendicular to a segment at its midpoint is called a perpendicular bisector. So it doesn't just have to be a segment, it could be a ray. What does that look like? You have a line, AB, and a ray, remember, has one endpoint and goes on forever in the other direction. Let's say this one, this is called ray, let's say X, Y. This ray intersected segment AB at its midpoint. So that means it cut it into two congruent parts. So this is, and let's say it's at a 90-degree angle. So this is also a perpendicular bisector, but it happens to be a ray that is also a perpendicular bisector. We could have a line or a plane. So a plane may look like, we have our segment AB. And a plane is, remember, kind of looks like a piece of paper. So let's say this plane, we can call the plane, remember, by one letter that's in the corner or by three letters. Let's call it PXZ. So plane PXZ is the perpendicular bisector because it's at intersecting the segment at a 90-degree angle. Okay, we're going to focus on the perpendicular bisector that is a line. This is line CP. It is a perpendicular bisector of segment AB. Notice the symbol for perpendicular. Perpendicular perpendicular symbol is like this. So line CP is a perpendicular bisector of AB. It split AB into two congruent parts and it's at a 90-degree angle. Great. Okay, another characteristic of a perpendicular bisector is that it's equidistant. Notice the word equi has the root word equal and distance. So a point at an equal distance from two figures, a point is an equal distance from two figures if the point is the same distance from each figure. So equidistance means same distance. Points on the perpendicular bisector of a segment are equidistant from the segment's endpoints. So an interesting characteristic that perpendicular bisectors have is that each point on the perpendicular bisector is equidistant to the endpoints. So point C is equidistant to B. Now if we were to draw a line from C to B, let's go ahead and do that. So I'm going to connect, we need it in a different color, not white. So if we were to connect C to B and C to A, the length of CB would be an equal distance as C to A. So CB is congruent to CA. That's just a property that all perpendicular bisectors have. Any point on this line is equidistant to A and B. So for example, if you put another point here and you call this point L, L is going to be an equal distance to B as it is to A. And we can see that if we draw a segment again. So let's use a different color this time. If I connect L to B and L to A, LB is going to be equidistant to LA. So let's do that a different color. LB is congruent to LA. So any point you can pick, it can even be down here. If you pick a point called X and we connect X to B and then X to A, XB is going to be congruent to XA. Notice each time I'm putting more tick marks, and it's just so that you don't get it, to show you that the length of CB is different to the length of LB, is different to the length of XB. They're not all the same, so they have different tick marks. But these are the same, that's why they both have 4 tick marks. The purple segments are the same, that's why they have 3 tick marks. And the blue segments are the same, that's why they have 2 tick marks. Okay. Let's look at our theorem, perpendicular bisector theorem. Of course, there's a theorem to almost every concept in this book. Theorems are very important, so make sure you are studying and understand your theorems. Perpendicular bisector theorem. In a plane, if a point is on the perpendicular bisector of a segment, then it's equidistant from the endpoints of the segment. Awesome. Well, remember, each one of your theorems is a conditional statement. That means it has a hypothesis and it has a conclusion. The hypothesis for this one is always after the word if. So if a point, let me fix that. We can highlight it. Let's highlight it. So I'm going to highlight the hypothesis. If a point is on the perpendicular bisector of a segment, then, so let's highlight our conclusion in purple, then it is equidistant from the endpoints of the segment. And that's kind of what we just looked at, except now we're putting it into an official theorem called the perpendicular bisector theorem. If CP is the perpendicular bisector of AB, then CA is congruent to CB. So these two are congruent, since this is a perpendicular bisector. Now let's apply that theorem to a problem. BD, or line BD, is the perpendicular bisector of segment AC. So segment AC is right here. Line BD is right here. And line BD is the perpendicular bisector. They want us to find AD. That means the length of AD. Well, if you notice, AD right now is 5x. So really what we need to do is find out what the value of x is. Well, as in any geometry problem, you want to use the given information to mark your diagram with the appropriate tick marks and or arcs. In this case, they tell us BD is perpendicular. So remember, perpendicular means 90 degrees. And the 90-degree symbol is a little box. So since BD is the perpendicular bisector, we need to put this little box right here. That means that's 90 degrees. We just learned from the perpendicular bisector that if a point is on the perpendicular bisector, then it's equidistant from the endpoints. So since this is the perpendicular bisector, point D is equidistant to A and C. So that means AD is congruent to DC. Since these two sides are congruent, I can take these equations and set them equal to each other. So I can do 3x plus 14 equal to 5x. And the rest is algebra. We can subtract 3x from both sides. This cancels. And we're left with 14 equals 2x. We can divide 2 to both sides. And we're left with x equals 7. Now that's not the final answer because they want us to find AD. So we'll plug in the 7 right here. 5 times 7 is 35. So AD is 35. Great. Let's move on. Now, of course, most theorems have a converse. The converse of the perpendicular bisector would be in reverse. If a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector. So if you notice, the perpendicular bisector theorem says if a point is on the perpendicular bisector, then it's equidistant. The converse says if a point is equidistant, then it's on the perpendicular bisector. So the converse is in reverse. The previous theorem's conclusion became this theorem's hypothesis. And the previous theorem's hypothesis became this theorem's conclusion. So here, in this diagram, let's say you weren't sure if CP was the perpendicular bisector. You can conclude that it is the perpendicular bisector by analyzing whether there are congruent segments in the diagram. So for example, because PB is congruent to PA, we know this is the midpoint. And if we extend CP, since D is equidistant to B and A, in other words, since DB is congruent to DA, we know by the converse of the perpendicular bisector theorem that line CP must be the perpendicular bisector. Let's apply that to an example. In the diagram, WX is the perpendicular bisector of YZ. So you can always go ahead and extend the perpendicular bisector. A. What segment lengths in the diagram are equal? Well, if WX is the perpendicular bisector, then XY has to be congruent to XZ because X is the midpoint. If this is the perpendicular bisector, then YV has to be congruent to VZ, and it is. They're both 25. It says, is V on WX? V is on WX because we extended it. If you remember, before we extended it, it was like this. But you can always extend your perpendicular bisector, and you will see that V is definitely on the perpendicular bisector.